Hello, we are Jakob, Arthur Louis,
and Vesna.
We will tell you something about cyclogons.
Imagine you're riding a bike in the morning, just like any other day. The sun is shining, the birds are singing. Well, you get the picture. What makes this bike ride special is that you ran over a piece of gum. Perhaps you were admiring the birds. Now you're probably asking yourself, why is that so special? I run over gum all the time. Well, what's changed is that, surprisingly, the first thing that crosses your mind is how far the gum has actually traveled. Even stranger, you wonder how far the gum would travel if your wheels were triangles, squares, or some other shape. But now we have a problem. It turns out that for some reason you have no idea how to do this. In fact, this troubles you so much that it ruins the rest of your bike ride, and perhaps even the rest of your morning. That's where we come in. We're here to make sure you're never forced to go through something like that, and now we're going to show you how.
We decided that a good place to start would be to draw a couple of these shapes and trace a line following the path of the chewing gum, represented by one of the shape with its verticals. This allowed us to calculate the exact route of the gum for any regular polygon we might wish to attach to our bike. Of course, this method is terribly impractical, especially since we would have to redesign the algorithm each time we wanted to change our wheels. So naturally, the next step was to define a method that would work for any polygon of our choosing. With a bit of work and a lot of caffeine, we managed to derive a formula that utilized complex numbers to get the job done.
So, I think it's about time we got down to the real nuts and bolts of our solution. The best way to visualize what we're trying to accomplish here is with a concrete example. Let's take the simplest regular polygon, an equilateral triangle, a shape I'm sure you're all familiar with. If that's the case, then you shouldn't have any trouble imagining this picture as a rolling triangle. You've probably noticed the path representing the movement of the vertex. This path is called a cyclogon and is made up of multiple circular arcs with different radii. Seeing as this is a triangle, the arcs are all of the same length and both radii are equal to the length of the triangle's side. We also note that these angles are all equal to 2 times pi over 3. Let us remind you that the length of the circular arc with radius r, determined by the angle phi, equals r times phi. Using this, we can calculate the length of the cyclogon made with a triangle with sides of length a equals 4a pi over 3.
To help us further understand the nature of a cyclogon, let's take a second to look at the route traced by a rolling square. Hexagon and octagon. With the help of these observations, we were able to progress to the next step of our project, which was to devise a general formula for the length of the cyclogon arc made by a regular polygon. How we managed this is something we'll describe in detail on the following slides.
First, let's take a look at these angles. Are they similar in any way? It turns out they're the same, but not just that, their size equals the outer angle of the polygon, which is, naturally, the angle by which every vertex of our shape pivots during rotation. These angles are equal to 2 pi over n, where n is the number of vertices in the polygon. As we can observe on this picture of an octagon, the lengths of all but 2 radii of the circular arcs making up the cyclogon are equal to the lengths of the diagonals of the polygon that we can trace from one of its vertices. The remaining 2 radii are equal in length to the side of the polygon. So we have n minus 3 plus 2, which is n minus 1 circular arcs.
Our next task was to come up with an equation to calculate the length of the diagonals. We've decided to try this with the help of trigonometric functions, with which we managed to prove that dk equals this, where dk is the kth diagonal of the polygon and A is the length of this side.
With the help of this and simple calculus, we were able to derive that Ln, the length of the nth arc of the cyclogon, is equal to this. In the process, we used complex numbers and Euler's formula. On this picture, we can also see the geometric meaning of this equation. Using this, we managed to simplify the sum that appears in our formula to this.
Finally, we must express the side A of the polygon with the radius of its circumscribed circle R. The result is visible here. As n becomes larger, the polygons become more and more similar to a circle. So, if n increases infinitely, we get the length of the cycloid, which equals 8 times r, where r is the radius of the circle.
So, there you have it. The next time your mind wanders from birds to cyclogons, you'll be able to solve the problem on your own and calculate the length of a cyclogon for any regular shape. I bet that not many people can do that, so don't be shy and feel free to impress your friends with your newly learned skills. I would like to thank you for taking the time to listen.